In the next few slides, we are going to lay the groundwork for inference in first-order logic. Consider the following sentences. For all x, fish x implies swims x, and fish Nemo. So we know that Nemo is a fish, and we know that all fish swim. How can we infer that Nemo swims? To get there, we need to basically be able to say that fish Nemo and fish X match. In order to do that, we have to introduce a couple of new concepts. We'll introduce substitution and instantiation, and we'll introduce unification. So a substitution is a mapping from variables to constants or to other variables. Let's say we have this sentence that includes the variable x. We can apply a substitution. We can substitute x with Nemo and obtain the following sentence. Fish Nemo implies swims Nemo. And here's another substitution. Here, instead of substituting x with a constant, Nemo, we substitute x with a variable, y. So after applying the substitution to fish x implies swims x, we get the new sentence, fish y implies swims y. Here's an example of a substitution. We don't have to have a single variable being replaced. We can substitute several variables at once, as long as we obey certain rules. So each variable can be associated with at most one expression. I can substitute x with a. I cannot substitute x with a and b, or a and f of b. And no variable with an associated expression can occur within any associated expression. So I cannot have a variable on the left side appear on the right side. So here's an example. I'm substituting x with a, y with f of x, and z with y. This is not a valid substitution because x appears both on the left side and the right side. It's being substituted and it's being used as a substitution. So this is not a valid substitution. An instantiation is basically a substitution of a variable with a constant. Here's an example. Fish x implies swims x. I can substitute x with the constant Nemo, and I get fish Nemo implies swims Nemo. So this special kind of substitution is called an instantiation. The rule of universal instantiation says that we can infer any sentence obtained by substituting a ground term, that is, a term without variables, for the variable. So this is how we write that universal instantiation rule. The sentence for all v alpha entails the sentence that we obtain by substituting v with a ground term g in alpha. Consider the universally quantified sentence for all x, fish x implies swims x. The universal instantiation rule tells us that if we instantiate that sentence with a ground term, such as Nemo, the sentence that we obtain is entailed. So fish Nemo implies swims Nemo is entailed by for all x, fish x implies swims x. Let's look at the second example of universal instantiation. Consider the sentence for all x for all y, rabbit x and turtle y implies faster x than y. So consider the substitution, x by Coco and y by Speedy. If we apply that substitution to our sentence here, what do we get? We get rabbit Coco and turtle Speedy implies faster Coco Speedy. So the rule is telling us that this last sentence here, rabbit Coco and turtle Speedy implies faster Coco speedy is entailed in the universally quantified sentence above. That makes perfect sense. If the sentence is true for all x and for all y, it must be true for Coco and Speedy. And here's another example of universal instantiation. Consider the universally quantified sentence. For all x, king x and greedy x implies evil x. Let's substitute x with John. Let's apply the substitution, x by John, to that universally quantified sentence. We get King John and greedy John implies evil John. We can also imply the substitution x by Richard. So applying that substitution, we get another sentence that's also entailed. And now we know that King Richard and greedy Richard implies evil Richard. We can also apply a substitution that contains a function. For instance, we can substitute x with father of John, and then we can generate a new sentence that's also entailed here. The sentence is King, father of John, and greedy father of John implies evil father John. So note that the three new sentences that we obtained by universal instantiations are all entailed by the initial universally quantified sentence. So universal instantiation can be applied several times to add new sentences to our knowledge base, and the new knowledge base is logically equivalent to the old one. And we have another inference rule called existential instantiation. Here the variable v is replaced by a single constant k, and it's important that k does not appear elsewhere in the knowledge base. The sentence there exists v, such as alpha, entails the sentence obtained by substituting v with k in alpha. Here's an example. There exists x, such as bird x and not flies x. So the existential instantiation rule tells us that we could replace x by a constant that does not appear elsewhere in the knowledge base. So let's use C1 as our constant. If we apply the substitution x by C1 to the sentence bird x and not flies x, we get the sentence bird C1 and not flies C1. The existential instantiation rule tells us that this new sentence, bird C1 and not flies C1, is entailed by the existentially quantified sentence, there exists x, bird x, and not flies x. C1 is a new constant symbol. We call it a Skolem constant. Let's see if existential instantiation works in this next example. For all x, there exists y, such as faculty y and advises y x. So in English, this sentence means everyone has a faculty advisor. Now, existential instantiation tells us that we can replace the variable y with a Skolem constant. So what happens here if we do that, if we just replace the existential variable y with a constant? We get for all x, faculty C and advises Cx. Does this sentence have the same meaning as the one at the top? And the answer is no. This sentence means that there is a faculty member, a single faculty member, who advises everyone. So the two sentences obviously do not mean the same thing. They cannot be equivalent. The second sentence cannot be entailed by the first one. So what's different here? The difference here is that the existential variable y is enclosed within a universal quantifier. There is this for all x in front of it, and the for all x makes things different. So we can no longer replace y by a single constant. We're going to replace it by a function of y. So this process is called scholemization. It's a more general form of existential instantiation. It allows us to remove existential quantifiers even when they are in the scope of universal quantifiers. So each existential variable is replaced by a Skolem function of the enclosing universally quantified variable. Note that we could have more than one variable there. So if I have a sentence of the form for all x there exists v such as alpha, I can replace v with a function of x. F is called the Skolem function, and the sentence that we obtain by applying the substitution v by f of x on alpha is entailed by our original sentence. So let's take a look at this example here. So we had our sentence for all x there exists y, faculty of y and advises yx. What we do is instead of replacing y by a constant, we replace it by a function of x, a Skolem function of x. So we substitute y with f of x. So this gives us faculty of f of x and advises f of x, where f of x could be the advisor function. So now we can write the entailed sentence for all x, faculty f of x, and advises f of x. We can apply scholemization when we have more than one universally quantified variable. Here's an example with two. We can have three or more. So when we have for all x, for all y, there exists v, we replace v by a function of x and y. If we had three variables, x, y, and z, we would replace v with a function of x, y, and z. And f in this case is also called the Skolem function. Here's an example with two variables. For all x, for all y, there exists z such as friend xz and friend yz. So the universally quantified variables are x and y. These are the variables that I'm going to use in my Skolem function. And the existentially quantified variable is z. That's the variable I'm going to replace. We replace z with f of xy in alpha. So we get friend x f of xy and friend y f of xy. So you can think of the f of xy function as the common friend function. Once we apply the substitution to our alpha, to our sentence that's existentially quantified, we know that the following sentence is entailed. We can now write for all x, for all y, friend of x, f of xy, and friend of y, f of xy. So in summary, scholemization consists of removing the existential quantifiers from sentences. In general, each existential variable is replaced by a Skolem function of the enclosing universally quantified variables. So here's the example. For all x, x is my universally quantified variable. There exists y is my existential variable, and I'm going to replace y with a function of x. Now, if there is no enclosing universally quantified variable, scholemization is simpler. Instead of a Skolem function, we have a Skolem constant. So we simply replace the existential variable with a constant. Now that constant must not be defined elsewhere in the knowledge base. Our next concept is unification. And unification is the process of determining whether two expressions can be made identical by appropriate substitutions for their variables. This is the notation. We'll say unify alpha beta to denote a unifier, that makes alpha and beta identical. So let's theta be that unifier. Alpha with the substitution theta applied to it is equal to beta with the substitution theta. We'll see some examples to make sense of this. So let's consider the expressions P of A, Y, Z and P of X, B, Z. To unify these two expressions, we look for a substitution that makes them identical. So you can see that if I replace X with A and Y with B, I get a unifier. I can also replace Z with C, and I also get a unifier. So both of these, X by A, Y by B, and Z by C, and X by A and Y by B are unifiers for these two expressions. Now the second one is more general than the first one. So let's work through some examples here. Let's say I have the two sentences, knows John X and knows John Jane. And I'm looking for a unifier. So remember, a unifier is a substitution. So I want to find a substitution that makes these two sentences identical. So the unifier here is the substitution that replaces X with Jane. How about this sentence? Knows John X and knows Y Anna. How can we make them the same? What substitution would make these two sentences identical? Well, we can replace Y with John and X with Anna, and then we have our unifier. How about this sentence? So it looks like we should replace Y with John, but we cannot replace X with mother of Y because then we get an invalid substitution. Remember the rule about not having one variable on both the left side and the right side? Well, we cannot substitute Y with John and then use Y in the substitution. So what we have to do here is we have to use the substitution Y by John and X mother of John. So this substitution will work. This is a valid unifier for the two sentences. How about this sentence? Fish X and swims X and fish Wanda and swims Y. So we can substitute X with Wanda, and we have our first expression, fish Wanda and swims Wanda. Now to make that identical to the second expression, we're going to have to substitute Y with Wanda as well. So our unifier here is X Wanda, Y Wanda. How about these two sentences? Knows John X and knows X Anna. Well, if we substitute X with John, we cannot also substitute X with Anna. There's something wrong here. We cannot find a unifier. So what do we do? What we do is we change the variable in one of these sentences. Remember, these sentences are true for all X. So for one of them, instead of for all X, we will use for all Y. So we standardize a part. We basically eliminate the overlap of variables, and we use Y in the second sentence and X in the first one. And now we can easily find a unifier. So today we introduced first order logic. We talked about the syntax of first order logic, and we introduced some examples where we saw how to translate English sentences to first order logic. We also introduced some concepts that will allow us to apply inference rules in first order logic. We talked about substitution and instantiation. We saw that we can use universal instantiation as an inference rule, and we saw that we can use existential instantiation, also known as columnization. And finally, we introduced unification, which is the process of finding a substitution that makes two expressions identical. Next week, we'll see how to build on what we've seen today to apply resolution in first-order logic.